that. And then you have replaced this silicon with arsenic, then you're going to have electrons, something like that. And then that ionization energy can be drawn in the conduction band and the valence band. Like from the distance from here to here, that is the ionization energy for the donors. And the distance from here to here is going to be ionization energy of the acceptors. Once it is ionized, then it means that this hose is freely moved in this system, and also this electron is freely moved in the conduction band of the system. So there is a very good probability for this electron to be combined with this hole. So it becomes a norm. That is going to be called the compensation. And if you draw that in a flat band diagram, what you can do is you can just moving electron to this acceptor, something like this. And in this flat band diagram, it seems that this is a huge energies for that. Okay, but in reality, this is not the real distance, the compensation, the energy necessary for the compensation. This is not the representation of the energy necessary for the compensation reaction to happen. And in most of the semiconductor devices, that compensation happens all the time. And why do we do that? Sometimes we want to have a very high resistance materials. Then in that case, we have to dope the silicon with a very small amount of dopants, right? But as I showed in the example, 10 to the 17th is already very small amount. And if you want to have a high resisting materials, then if you have to put less than 10 to the 17th in the silicon evenly, and that is very, very difficult. So in that case, what normally practiced in the industry is that you put a certain amount of phosphorus, and at the same time you put a certain amount of boron, so that the small difference in the concentration will reveal the conductivity of the material. In that case, you can have the free carriers less than 10 to the 17th, let's say 10 to the 16th, or something like that, in a controllable manner. So if you want to have if you want to add a very small amount of a dopant in the semiconductor, what you can do is you can do this compensation phenomenon. You can use this compensation phenomenon. Okay, what time is it? Okay, and next Monday, we're going to talk about the Hall effect, and then a little bit of front part of the magnetic properties of the solids, and then on Wednesday, we're going to finish the magnetic properties to wrap up this class in this semester. All right? Okay, just to confirm, remember that we're going to have a final on the 13th.